So guys, we're going to do this uniform circular motion activity in which the purpose is to explore the different characteristics of the motion of an object that is in a circle at a constant speed. So right off rip, what is velocity? You guys remember? Just the definition. Velocity is speed with a direction. Like, so we have, it's moving 4 meters per second east, or it's moving, negative 30 meters per second. The negative is indicating a direction. So with all of that, okay, if you're moving at a constant velocity, technically you are in a state of equilibrium because everything has to wind up balancing out. So can an object be moving in a circle at a constant velocity? Yeah? Okay. So if I, like yesterday, right, if I spun, I just take my keys and I spin my keys around. So is that a constant velocity? Why? So if it's moving at a constant speed, right? So remember, velocity is speed, pretty much speed with the direction. As it's going around in a circle, it is constantly changing direction. Therefore, its velocity is constantly changing. So you cannot have a constant velocity and be going around in a circle or any kind of turn or anything like that. But you can have a constant speed. So you got to make sure you make that separation, that difference. So the first one is just basically telling us to navigate with the tools and the animations itself that can be started, paused, continued, rewound. So I put the link in there in the assignment for you guys. I'm just gonna do this here. So this little plus sign is our center, and we can hit start. Given the values here, all right, we got some kind of motion. Now we can click on these buttons over here to show the vectors. And remember that the velocity at any given point is tangent. So at any given point, all right, this seems to all be rotating around clockwise. It wants to make a straight line path. It wants to get out of here. So like in the ball going around the cup, or I'm sorry, the ball going around the plate yesterday, when we had that little piece missing, while there was no force keeping it in its circular path, it flew off in a path tangent. So that's what this tangent vector is here, all right? That's the velocity vector. Force, we said yesterday, we talked about, force is always pointing towards the center. Because without a force directed towards the center, nothing's going to be able to continue moving in a circular path. And by Newton's second law, accelerations are in the direction of the net force. So if the net force is directed inward, the acceleration is directed inward. So we can start and stop this at any given point, and you'll be able to see that the acceleration is always pointing towards the center, that plus sign.
Is it possible for it to be outward?
An outward force?
Yes.
It's not, because then it's not going to be able to stay in a circle. All right, so if you were trying to keep something like that in a circular path, right? So when I was trying to move the ball around yesterday in the circle, I had to keep the ruler on the outside of it, trying to keep it from going away. Because if I put it on the inside and applied any kind of force, it was going way outside of the circular path. But that is definitely a good question. So 2, right off rip, vectors, a quantity that has both magnitude and direction. Using complete sentences, describe the object's velocity. Comment on both magnitude and direction. So let's see. So we're going to basically describe the velocity of this object. So if you guys are looking at this, I'm going to turn the velocity vector on. I'm going to increase the speed. I'm going to decrease the speed. Look what happens to the magnitude of this vector. What happens? As I increase my speed, what happens to the magnitude of the vector? It increases. It gets bigger. Okay. So now with that being said, Let me slow it down just a tiny bit. Oh, 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 oh. Okay. What do we notice about this? Right? Vector that has both magnitude and direction. Use complete sentences. Describe the object's velocity. So comment on both the magnitude and the direction. So what about the magnitude? Is the magnitude, like the length or size of the arrow, is that changing? No. So that's indicating what? A constant speed, right? It's indicating that a number, that value, which I guess we have right now set us at 24. So that part of it is not changing. But what about the direction? It's exactly right. It's constantly changing. Okay, so you're going to put something along those lines in there for your answers, or for that answer. Now, number 3, if an object moves in a circle at a constant speed, its velocity vector will be constant. And then you explain your answer. Well, again, I would say that the magnitude of the vector didn't change because the speed didn't change, but the direction was constantly changing. So that is pretty much what this is showing. This is telling me, if I were to look at this, all right, the size of that arrow is never changing. So that tells me that it is moving at a constant value, whatever the heck it is. In this case, we set it set at 24. But the direction, that is constantly changing. So again, it's very similar to that answer as the first one. Its velocity vector will be constant. False. The reason why is because the direction is constantly changing. Remember, velocity is like we said in the first one, is speed with the direction. All right, now for number 4, I'm going to zoom in just a tiny bit. So for number 4, in this diagram here, they have a variety of positions indicated by the circles or these little dots here. They want us to draw the velocity vector at the various positions, and they want us to direct the velocity arrows in the proper direction and then label them as v. And then they want us to draw the acceleration vector at these different positions, put them in the proper direction and label them as a. So what we're going to do, first I'm going to go to shapes. I'm going to go to insert line. Somewhere in the center. It looks close enough to the center. I'm making a little plus sign. To me, that looks center, right? Solid enough. Now, we're going to say that just like in the simulation, this thing is rotating clockwise. So you can do one of two things. You can try and go to the simulation and pause it like at approximately these different points here, or know that if we're going around clockwise, so I'm just going to make it edit here. So what clockwise is telling me is that it's doing one of those. That's kind of how this thing is moving around, is spinning around. So if I sent this out and I put on the velocity and the acceleration vector, velocity is tangent at any point. Okay, it's going to want to fly off tangent. It's going to want to try and move in a straight line. Okay, when we again the plate example yesterday, when that piece of the plate wasn't there, there was no longer a force keeping it in, and what did it do? It moved in a straight line. So at any single point, this object is trying to move in a straight line, and it would fly off tangent to where it is on the circular path. And again, yesterday we talked to like a tangent line is just, let's go red for velocity. So I would go right onto this first circle. If it's going around clockwise, it's going to want to, right, like it's going to be doing one of these, moving as it's moving around. It's going to want to fly away. And from the interactive that we did yesterday as well, from physics classroom, there was a thing on there that showed, let's make it about there, not too long. Okay, I'm going to make myself a little arrow. That's awful, arrow. So that would be velocity. What about the next one? Oh, wait, we got to draw in our acceleration vector. We can do that. We can do all of them at once, or we can just do rotate around. What color should I make this guy? Yellow, green, purple. Let's see what the green looks like. Okay. So this is going to be pointing, again, towards the center. This dude here. And that is going to be our acceleration. And I will just put a little text box there for that one. So the next velocity vector should look like what? It looks like this is approximately at like 2 o'clock on a dot. So let me see if I can get this to, it's close enough. So this is what it should look like. Again, acceleration pointing center, velocity tangent. Not make it too big. It's probably like about there. It looks solid. So we're drawing our velocity vector there. So we have velocity again. So I'm just going to just continue on and make the velocities here. And then we have our acceleration. So at any one of these points, they are pointing inward towards the center. Now, if we were to use a force, draw in a force vector as well, what direction would that be going? Good, to the center. So this, guys, is what your final product should look like. So leaving 4, let's move on to number 5. Describe the relationship between the direction of the velocity vector and the direction of the acceleration for a body moving in a circle at a constant speed. So what is the relationship between the direction of the velocity vectors and the acceleration vectors? So based off of looking at what our final product here looks like, describe that relationship. How is the velocity vector being pointed? Now, we've said it a couple times already in this lecture, and the same thing for acceleration. So tell me, what is that relationship? What's going on? What direction is the acceleration always pointing? Inward, towards the center. And then how is the velocity vector acting? Straight line. Straight line begins with the T, A, N, tangent. All right, so it's in a straight line, tangent to its path. So everyone should have been done with 5. Now, a puzzling question to think about: if an object is in uniform circular motion, then it is accelerating towards the center of the circle, yet the object never gets any closer to the center of the circle. It maintains a circular path at a constant radius from the circle's center. Suggest a reason as to how this can be. How can an object accelerate towards the center without ever getting closer to the center? Something in the way of it. Okay. Well, okay. So why does something move in a circle? Yesterday we did all those little demos. What was causing something to stay in a circle? Yeah, a force. And by that, acceleration goes in the same direction as the net force. So wait a minute, if the force is directed inward and the acceleration is directed inward, why isn't it moving inward? How is it moving in a circle? Well, see how like the velocity wants to fly off this direction? Well, the force is essentially keeping it from flying off, and the acceleration has to be in that same direction. Now, even though it's not necessarily speeding up, remember there's 3 ways that we can get an object to accelerate, because acceleration's definition is a change in velocity over time. Now, our speed is not changing, but how is our velocity changing? A changing direction. So, if our velocity is changing, therefore we have a change in acceleration. So a change in velocity is a reason, right? Change in direction is the reason why we have an acceleration, even though it's not going to be speeding up or slowing down. It's not accelerating towards the center per se. So I think it shows it kind of similar here. In this, as this was going along, if you were at point A and this thing is moving around clockwise, at point A, it wants to go to B prime. But as it makes its rotation, it stays where B is. And that has to deal with the fact that our force is always going to be directed inwards, like our acceleration. So they would both they're pointing inwards towards that center. So the force is basically keeping it from flying away, and the acceleration is in that same direction as our net force. So it's, even though, right, the velocity wants this thing to go off and away, it is that force, that acceleration, that is keeping it in this circular path. So it's not getting closer or farther from the circle for that reason. So now for 7, suppose an object is trying to move clockwise in a circle, or at least trying to move in a circle. Suppose at point A, the object traveled in a straight line at a constant speed towards B prime. In what direction must a force be applied on the object to get it to go back towards B? So draw an arrow on the diagram in the direction required of the force. So let me zoom in just a little bit more here. So if the object is going from A to B prime, but it doesn't actually make it to B prime, it goes to B. What direction does the force need to be from B prime to B? So if I drew my arrow out this way, is it going to go from B prime to B? What about this way? No. What about this way? No. How does it have to go? Inward. Bingo. What's his name? So since that force needs to be directed inward, that is the acceleration that follows. The acceleration is in the same direction as our net force. And then the same thing for C to D prime, but it doesn't actually go to D prime, right? Even though the velocity, again, wants to go in a straight line, it's not doing that. And why? Because there's something causing it to change direction. What direction would it need to go? Again, inward, going towards the center. So our forces are directed inward. So then they finally ask, if the acceleration is towards the center, so I'm just going to add myself a little plus sign here. That's not quite the center. It's annoying me. If the forces, or I'm sorry, if the acceleration of the body is towards the center, what is the direction of the unbalanced force? Using a complete sentence, describe the direction of the net force that causes the body to travel in a circle at a constant speed. Well, if the acceleration is towards the center, what direction does the net force have to be? Towards the center, because the accelerations are always in the same direction as your net force. So in some form of a complete sentence, all right, you'll write that in. All right, so now we're going to move on to thinking mathematically. So now we're going to go back to this simulation. We're going to explore the quantitative, which has to deal with numbers. So we're going to deal with the quantitative dependencies of the acceleration upon the speed and the radius of curvature, and then answer the following questions. So for the same speed, the acceleration of the object varies, blah, directly or inversely with the radius. So how is the acceleration going to be affected as we change the radius? All right, so we're going to leave the speed the same, and we're going to look to see what happens to acceleration if we mess around with the radius. All right. Also, they just said don't touch the mass, so we're going to leave the mass the same. And right now, the acceleration is at 13 meters per second squared. Okay. I'm just going to throw the velocity vector on and the acceleration vector. So if we're watching this, going on, this had changed the radius. What is going on with the acceleration as the radius gets smaller? We were originally at a radius of 30. As we shrink the radius, as the radius decreases, what happens to the acceleration? It increases. Okay, well, let's say we went back to original. All right, our acceleration is 13. Now, what if we increase the radius? Let's go to 40. Now what's going on with the acceleration? It's getting smaller. Oh, it's decreasing. So as radius increases, acceleration decreases. And as the radius decreases, the acceleration increases. Hopefully I said that right because my ADHD here. But as one goes up, the other goes down. So that is a what kind of proportion or relationship? Inverse. All right, inverse. Directly would mean whatever happens to one happens to the other, which is not happening here. Get it? All right, nope, sick. So yeah, we can do highlights. Oh, screw that. We can do shapes. Let's go circle, and let's go swoop bam inversely. So now we're not going to touch the radius. Let's see what happens to the acceleration as we change the speed. So keep the radius the same. Now let's change the speed. Let's see, reset this piece. Let's turn both of them on. Let's hit start. And so this wants to know what's going on as we change speed, correct? All right, I'm going to decrease speed. What happens to the acceleration? It decreases as well. Okay, so the original was 20. Now, what happens if I increase the acceleration? Increase the speed. What happens to the acceleration? Oh, it's increasing. Oh, yeah. It's increasing for shizzle. So, as speed decreases, acceleration decreases. As speed increases, the acceleration increases. So that would be a directly proportional relationship. Circle. Bam, bam. Okay, now, as the speed of an object is doubled, the acceleration does what? Is it 1/4, 1/2, 2 times, or 4 times the original value? Okay, so let's go back. Let's keep this piece at the ridge. The original value here, 13 meters per second squared. So they're asking us, as the speed is doubled, what happens to the acceleration? So if we can't really double this, right? It only goes up to 30. So let's go to, let's see, it's 15. All right, let's set this, let's just say 10. All right, so at 10, our acceleration is 3 meters per second squared. So what do they ask us to do? They are going to ask us, speed is doubled, what happens to the acceleration? So we're going to change speed from 10 to 20, right? We're going to double it. So the acceleration at 10 was 3. What is it going to be at 20? 13. Okay. So what's 13 divided by 3? What's 12 divided by 3? 4. So it's a little bit over 4. So what happens? Yeah, it was 4 times its original value. As the speed is tripled, the acceleration is what? Okay, so when we had it at 10, we were at what speed? Or we were at 10 meters per second for growth of speed. The acceleration was 3 meters per second squared. So what's triple of 10? 30. So let's move this to 30, see what happens. Acceleration is 30. 30 divided by 3. 10. Just that's technically not an answer. All right, it's going to be 9 times. So some of these values may be just slightly off due to rounding things here. But based off of what we're going to do, we're going to come up with an equation. We're going to come up with an equation. All right, next one. As the radius of the circle is doubled, what happens to the acceleration? All right, so let's reset this. Let's keep this here. And what did it say? The radius is doubled. So what does this go up to? This goes up to 60. So we could do 20. All right, so at 20 meters as a radius, what is our acceleration? It's at 20. So again, they wanted us to double the radius and then see what happens to the acceleration. So double of 20 is how much? 40. So at 20, we were at 20. And at 40, we're at 10. So how did yeah, it went down by half. It got cut in half. What if this radius was tripled? What if the radius of the circle was tripled? All right, so we were at 20 meters per second squared when we were at 20 meters. So triple of 20 is 60. Here we're at 7. This is on the round hook. 40, 20. So at 60 meters, it said we were at 7. So original value was 20, 7 over 20, a little less than 1/4, but no, 1/3, right? Yeah, that's approximately 1/3 because 6.66 repeating, if you round it up to 7. So we're looking at, okay, then 1/3. Oh, that's annoying that it's not here. Just because the one part of it is here and the other part's there, that would bug me if I just try to circle it. Okay, so write a conclusion to this activity in which you completely describe the characteristics of an object that is traveling in uniform circular motion. Give attention to the quantities speed, velocity, acceleration, and net force. Okay, so specifically, let's take a look at acceleration because this is what this piece was talking about. When I doubled my speed, what happened to the acceleration? It went to 4 times. When I tripled my speed, what happened to the acceleration? 9 times. Does that have any relationship to you, do you think? Close, you just can't think of it? So how is the number 2 and 4 related? You add 2 together, you get to 4, you multiply 2 to get to 4. Oh, and then how is 3 and 9 related? Squared. So the acceleration is going to equal the velocity squared. And how is it related to the radius? When radius got bigger, did the acceleration get bigger? No. So the direct relationship is basically as one increases, the other increases. One decreases, it decreases as well. So the acceleration increased as velocity increased, but it increased with the square of the velocity. So this is how you can figure out part of the equation. So the acceleration for an object moving in a circle is equal to the velocity of that object squared. But how is it related now to the radius? The radius, as radius got bigger, right? It doubled. What happened to the acceleration? Got cut in half. If radius was tripled, what happened? It got cut into 1/3. So that would be basically just saying, okay, I'm dividing by the radius. You're dividing by the radius there. So you just basically figured out an equation for your for this piece here. All right, the acceleration for an object moving in a circle, all right, at a constant speed. The acceleration is the velocity or the speed, velocity, squared divided by r. And they asked also about net force. Okay, so the net force is down here. Okay, so let's just say this. Net force is 17. If we double the speed, what happens to the net force? It went from 17 to 67. That is approximately 3.94. So did it also increase by the square? Just like the acceleration did? Yeah. What if we tripled it? So if we went up to 30, and this 150 divided by the original 17 is 8.8 and change, which is approximately 9. So just like the acceleration, centripetal force is increasing by the square. So centripetal force is going to be directly related to the speed, and it's going to be to the square. How does this affect the radius? As radius decreases, net force increases. So that as well is inversely related. And then how is the mass related? As the mass increases, so does the net force. As the mass decreases, so does the net force. So that equation then would be this very similar to this. All right, the force is equal to the mass times v squared divided by r. Or sometimes you can then rewrite it as the force is equal to, technically we should be using the subscript c for centripetal. The word centripetal means center seeking, so it's center, circular motion acceleration, circular motion force. So basically you can then rewrite the centripetal force as this. Centripetal acceleration, MAC, right? Mass times acceleration.